Welcome to Security Management for Critical Infrastructure. My name is Christopher Gorog, and I will be your instructor for today. This course covers more in depth on the topics we introduced in the Introduction to Security Management, including contrasting the difference in security basis, defining security management areas, business management and security management gateways, bridging the gap between network types, an overview of each of the security management areas, and the follow-on courses. Contrasting the basis of security. In this section, we're going to look at the difference in security basis between information technology systems and industrial control systems. We displayed this image in our last course to kind of give you an overview of the stalemate we have between these two different technologies and technology areas. This basis of security difference at its highest level starts with information technology systems being designed around the behavior of humans and industrial control systems being designed around the behavior of machine-to-machine communications. Humans have asynchronous behavior. An example of this would be the user initiates some actions. Transactions begin in irregular patterns as the user decides to do them. Then actions on systems somewhere else are taken in a background process. Wherever the system has time to complete them, works on them. Systems store action data and then process it later whenever they need to. And events are processed in order they arrive at the resources and as resource utilization permits. Each event has different sized data items based on the needs of that user at that particular time. Synchronous computer system operations have continuous packets of the same size. Data is broken up to fit into the size of these packets, and that way it's known predictable times for each communication between the locations. And you're able to calculate the time for each signal to pass between any 2 points on the network because you know exactly how long it takes. Communications are either two-way or alternate back and forth, so send one way for a certain amount of time and back the other way. Now, contrasting these two, asynchronous behavior of humans versus synchronous behavior of machines, we'll look at it from the IT industry and from the industrial controls industry. And IT has been developed around this asynchronous behavior of humans, where industrial controls require that synchronous component to communicate. People don't mind if the same operation takes a different time to complete each time. Actually, they don't even notice it or have a tolerance for it, and a lot of times you'll start something and expect to come back to it later. User interface applications are designed around triggering operations and waiting for them to complete. So people just have this understanding that that's how it's done. Operations are input into a list called a queue and then processed as time permits, and operations, the actual processing time is time sliced. So data then is a variable length because each human creates a file or its work at a different time is a different size. Because of the file size, there's going to be a difference in the time it takes to operate on these files. Industrial controls, they operate electromechanical equipment such as factory assembly lines, robotics, or breakers out on a power distribution. Controlling electromechanical operations requires each transaction to take place in less than a certain amount of time. Now that time might vary for different types of equipment, but it has to be known and predictable. Each operation relies on verifying that the other or another operation has completed, and operations are in order and required positive verification of the last before starting the next. So if two mechanical arms are doing something, you have to know that the last one was done before you start the next one. And a lot of times this is done in times that are faster than humans can even fathom. Data for these commands has to be in a fixed length, so the communication size and time has to be known so they can determine that it was done in a certain amount of time. Here's a visual depiction of another concept that is ingrained in this asynchronous versus synchronous behavior, and that is the structured transport versus dynamic transport. You see on the left I have a railroad car showing a structured transport, set size containers, set path. You must trust that path because the train's going to go down it. And if it derails, it causes a problem. On the right, we have a dynamic transport, which is more like a highway system with trucks on it. Variable size content, variable path. If one road's down, one path is down, it doesn't matter. The truck driver makes an independent decision to find another. And this is kind of a difference when you see how IT networks have been established over time. It's this dynamic transport versus industrial controls uses structured transport. Next, a primary use of storing and accessing data versus a primary use of controlling machines. The primary concern for IT systems is to separate, secure, and provide authenticated access for each user to their data. So it's all about the people and the data. Control systems' primary concern is for security is operational availability while providing high accountable authentication of devices. So making sure that those commands can be trusted, and making sure that the network can be trusted. Data on an IT system is the primary focus. Data can be replicated on several systems or backed up on physical media. It doesn't really matter. The value of an individual system is irrelevant as long as the data is retrievable. Systems on a control system network are online continuously. A single down system disables all other dependent systems or downstream systems. Constant verification that each device is available and reliable is part of security's function in these type of networks. Now, since data is the primary focus on IT systems, we look at embedded systems. They don't really even have a concept of data. There's not really data required, and data storage is not something that is thought about when those systems are designed. In IT systems, applications are stored in memory when they're not being used. Applications and user data is stored on systems, in databases, on media, in the cloud, anywhere, all these different types of areas. As long as the data is retrievable when needed, it doesn't matter where it's located. Embedded systems, the system microprocessors have very limited capability. Talking a lot of them are measured in kilobytes. Code for operation is only thing stored in memory in most cases. They do the same limited list of tasks repeatedly over and over again. The only thing stored that is important to them is the status, the current state of that machine. Any data stored or transmitted is the same structure and often the same exact data relating to a separate operation at a different time. So now time becomes a focus. Data storage systems versus control systems. Information technology systems store users' data. So it doesn't matter what media stores the data or how many computers handle the transport. See, I'm showing a diagram of data could go all these different directions. It doesn't really matter. Stored on media, stored in the cloud, stored in a database. As long as data is recoverable and is protected and separated from other users' data, that's what's important in IT information storage. Industrial control systems are more like the microwave or the coffee pot, where they perform a single set of tasks which require limited output and input. Data is not stored about past events. It doesn't care what happened in the past. It only cares about is the current state of the machine. That's the only thing really of interest, how much time is left on the clock and the countdown until that time is done. Data related to their operation is only of value in aggregation, so only when it's collected with other systems or related to the time of operation of a particular event. So knowing that a coffee pot is in the state of brewing coffee or has been in the state of brewing coffee is not important as knowing that it was brewing coffee at 12 p.m. last night. Events related to control systems are collected in the attached IT data systems, and where the data storage is done is on the IT side. And then it looks as another user creating data that goes into an IT system data storage. Another contrast and security basis is IT systems support users. And IT systems only exist for users to interface virtual items consisting of data. And control systems are independent of users. Many control networks operate without any users entirely. So without a user, there's no need for an IT computer. It just sits there. Servers that are manned by administration staffs only exist to store multiple users' data. On the control network side, thousands of machines are on a single network. Critical infrastructure networks, each node operates for years without a human being involved, just continuously running its state and doing its particular operation. Only user operations are for maintenance or fault repair. Something goes wrong is the only time a user really has to come into the picture. Look a little bit at disruptive communication attacks and why they're so important in control systems. This is another difference in security basis. On a control network, communications are passed from node to node on a network to operate, see this end node. When operating electromechanical equipment, disruption of communication can be a malicious activity in itself. Taking down a critical infrastructure network can cause physical damage, human injury, or economic loss. These type of attacks are known as black hole attacks. Selective filtering, malicious activity can monitor communications passed on the network, just sit there passively and listen, checking for certain types or destination of operations. See, this operation was detected by this middle node and was supposed to go to the end. So when a command is received, which the malware on there wants to affect that change or rewrite, it either selectively eliminates or reroutes that particular command, changing the operation of a critical infrastructure network. It can cause physical damage, human injury, but are usually designed to affect economic events, something more selectively done to gain by an individual making such malware. These type of attacks are known as gray hole attacks. So trusting systems and networks, trust starts with the person that can be held accountable. We trust IT systems because they are directly linked to human users. Industrial control systems operate for years, in some cases without human involvement whatsoever. They consist of unmanned networks of utility sensors, robotics, or automation-controlled micro-devices. So the next basis of security difference is system trust assumed with the user versus established trust of an ecosystem. IT systems rely on environmental parameters of the machine and assume that the physical boundary is an extension of that user and thus is uncompromised. So that assumption is that this computer or laptop or desktop is in the control of the person. So now we only need to worry about its connection to the outside world and its software operating on it, because we trust that the human that owns it is responsible for it and is not going to go digging into it and try and circumvent its operation physically. So human sits at each system and controls its physical trust associated with that machine itself. Server equipment that is locked in a facility is extended the trust of that administration team and that company that secures the physical part boxes that do the work. In IT systems, the nodes that transmit or route, trust for them is irrelevant as long as a user can have a method of trusting the destination device, verify the completeness of the data after storage or transmission, know the storage location to be able to retrieve that data. They can always just encrypt the information while it's in transmit or being handled by those intermediate routing devices, and they really don't have to trust them. Industrial control systems rely on high accountability that control commands are authentic and the communication systems are trusted. Traditionally, these devices have been on private networks owned and controlled entirely by the organization or companies. Signals passed along the network need to trust each system that passes them to operate that electromechanical command. Entire networks need to extend trust of the organization and not just one system extending the trust of the user. Trust needs to be established by having an entire ecosystem controls. Starting in development and manufacturing, establish a method of trusting the root operation of that device. Through distribution and supply, logistic operations to verify trust capability is passed to the end user or passed from organization to organization as it goes through the distribution chain. In networking and provisioning, has to extend the organizational trust to the networks. So take that trust that was established during development and manufacture and transfer to distribution and supply and link that to operational network and provisioning that device to the network. And then during operation, maintain, improve trust within and between the organization and for the network. The next area where security basis is different is in the size and complexity of the applications and the code. Exploiting simple control system operation software, designers try to use the smallest microprocessor, which will do the job because of the expenses. It's cheaper. Code extraction is often trivial, and if code is easy to take out and look at, now key extraction attacks become a risk. You see in this image I have the recognizable patterns in memory, and the one circle or boxed in red has an even distribution of bits, and this would be a key stored in this minimal memory, and this is targetable by attackers because of its even distribution. They look for these patterns in order to implement a key extraction attack. So code is closely tied to memory locations and the allocation of memory. Debug ports in these systems are hardwired into either the microchip. A lot of times that extends into designs and has a plug right on the side of the actual system. Memory is often in kilobytes or megabytes, so very small size in relative to IT systems. IT systems are built on expandable memory models, obfuscation of data, and white noise reduced restriction attacks. By white noise, I mean the overall magnitude of everything out there is so large that to look through it for a particular thing is difficult because there's so many other things blocking that attack. In this large data model, the protected network servers provide backup capability. There's just an incredible amount of data out there, and the complexity is at a much higher level than with industrial control systems. The next area of contrast and basis of security is an IT system runs on virtual machines and allows anonymous systems to implement secure transactions between software at each end. And this is able to be done because of that trust, that accountability that's relayed from the user to the machine. Virtual machines, anonymous communications, and untrusted systems are kind of the nemesis of this high accountability, authentication, and system trust required for control networks. In a control network, if that communication is sent across several virtual systems, there's no real physical machine tied to it. And the ability to allow virtuality on a network becomes a danger to these type of systems. In the IT system, cloud computing designed to pool resources from anonymous locations and they allocate those resources at runtime. This is the whole kind of concept of cloud computing. So physical hardware systems connections to users, the concept of the PC is irrelevant. So it doesn't matter if the PC that you see virtually is connected to a physical machine or just a portion of several machines that you utilize the resources from. Operation of electromechanical devices requires trust for each system that's passing the command along. Virtual systems logically can be located on any network and look like they're somewhere that they want to be. Point-to-point tunneling can connect any system across any network to look like a local network. Virtual machines can be 100% copied and they can be operated from another location. This is a big danger to these networks that require trusting every device that passes electromechanical command. The need for availability and safety is the next security basis gap that we'll talk about. Industrial control systems are designed to fail in an available state. IT systems fail in a manner to protect data and data privacy. The only thing more important than availability in industrial control systems and network is safety. Safety of operations and protection of equipment is the only reason for taking a system out of operation. Safety is a top risk managed by operations departments. Users are not tolerant to downtime, especially when it comes to a power grid and power distribution. Restoration is the primary focus of operations, getting it back up and online. The users cannot work during downtime, so if there's no power, everybody serviced by that power is totally down at that time. IT systems fail in the manner to protect data and data privacy. Users are tolerant to downtime because they know it's protecting their data. It's better to lose time than data. Users can work on alternate items during downtime, so it's not really a problem not having anything to do. Time for restoration of disks and data is a risk managed by business continuity and disaster recovery. They prepare for system loss by backing up the data on a recurring basis. Data can be restored to another system and get it back working. So it's all a difference in perspective. It's not as important to get the current system back up as it is to get a new system that has a copy of the data back online. Another big divide in security basis is the expectations of users towards design cycles of these systems. IT users have learned to expect that computing capabilities should and will always expand. So if you're always going to be faster, better, more capable next time, you don't really think about utilizing resources in a sparing manner. Moore's law says that you're going to have twice the computing resources for the same cost with each cycle. So the next time you buy a new computer, the software you made that is barely able to support this or be supported on the current version is going to operate in lightning fast speeds. People have become accustomed to expecting that. So security designs and designs of implementation don't require looking at resources as a limiting factor. The assumption that the same task will always be easier and more streamlined next generation is a good example. Think of the solitaire card game. As you bought new computers and watching your Windows operating system or whatever run the solitaire, it got faster and faster and faster with each version of computers you had come out and each new software. And I remember one time picking up a new computer and watching the end where the solitaire cards would bounce, and it went so fast it was done, where back in the very early versions of Windows 3.1 that would bounce for 5 minutes until all the cards fell off the pop. In control system networks, they enable businesses to become more efficient. So designers are striving to provide long life expectancy on these devices and use the smallest device with the most minimal requirements capabilities to achieve a given functionality. And this is to reduce cost, because you're going to make millions of these, you want the cost to be lower. And they create efficient and stable code with minimal complexity. So taking complexity down is a big importance if you think back to assuming that the technology is going to be much faster next time. Creating efficient, stable code is not really something you have to think about. So the more devices on the network, the better the information gathering. And this is why they strive to have more and more and more devices. The more business trends can be gathered, the more data analytics, more efficiency and use to improve efficiency. There will always be a push to communicate with smaller, less capable microprocessors in each design cycle for industrial control systems. Get the next level of smaller devices, more efficient devices online. So the growth trends in engineering cycles are entirely different with the expectations and the basis of security designed into them. To define security management areas, I'm starting with a model that explains network types and different types of networks. And to look at it, we're going to use the Open Group Jericho Forum Cloud Cube model. This shows different types of networks referenced on a cube, showing 3 pairs of extreme different parameters: external versus internal networks, proprietary versus open, so open standards versus proprietary owned by a certain group or a certain company, parameterized versus deparameterized. Parameterized would be inside a company that owns, physically controls the whole network, and deparameterized, an open source network like the internet or a cloud model. What I'm going to do is break apart this model a little bit, and we're going to dissect it and how these different quadrants on this cube relate to each other. And to do so, I've broken it apart and I've labeled the labels on different, just letters on each block, so we can start talking about these different blocks and how the different parts interface with each other and how the different networks relate. Security management combines the technical aspects and the business aspects and relates to different network types and bridges the gap between them. It sets up controls for information passed across boundaries between these logical or physical networks. In addition to the different types of networks, we'll also look at the collection, what these networks are made up of. And for this, I have 4 different kinds of collections of networks that we'll talk about in relation through the rest of this training. The first is groupings of physical systems which communicate by wired, wireless connections, any way you can imagine. Things, computers that are networked, physical systems that we use to actually communicate across networks, either the internet, private networks, or company networks, or whatnot. The second collection type we're familiar with social media is networks of people that are linked for common purposes. The third type, we'll look at something that might be a little new to some people, but networks of families of products that are distributed over many end-use locations, but they all work together as complementary products in a chain of products either made by a particular company or made by an ecosystem of companies, but they're all meant to work together for the same end, collaborative use. And the fourth collection type is the ecosystem of companies or organizations that interact by business transactions. And these networks in business are all over the world, and we're familiar with these as well. We're going to look at these 4 different collection types, as well as the different network types that we talked about in the Cloud Cube model as we progress through this training. The first contrast we'll look at is this A block to B block. The A is proprietary internal systems that have a tight parameter. So, meaning in this case, physical components operating on industrial control systems are parameterized. The network has to be known, they're internal to the company, and they're usually very proprietary in their operations. And the other side of the contrast, B, is open standards, external to the company or external to the network, and deparameterized. And this refers a lot to kind of the cloud, which they use open standards. Resources are dynamically managed whenever they need to be used, and they're just out there, and you don't even really have a way to know where they're at and where you got them, maybe after the fact, but dynamically they're just pulled as needed. So this contrast is found in critical infrastructure to IT networks. As we talked about, they're nearly opposite in every possible way, as described in the basis of security back in the last section. Block A, the physical components linked to geographic locations. Block B, virtual applications such as cloud, separate from physical systems and use dynamic resource allocation. To bridge this gap, nearly every security management area must be addressed. Organizational, logical, physical, regulatory, process, protocols, and policies, all of them have to be addressed. This particular contrast is the main focus of the security management for critical infrastructure. We'll talk about this and come back to this in many different times. Looking at a logical and organizational contrast on the cloud cube model. Many vendors have security on supply chain logistics, which at least address parameterization in their supply chain, things such as control of location and tracking on products. But the end network users want to have multiple vendors provide products to work together. Thus, when they get these different product chains from different vendors, they bring them into their organization, and it breaks down the controls on the supply chain in order to enable multiple vendors to work together, because these vendors' products don't have the same tracking controls and everything across this industry. So you see, you have this contrast from C to D, where external products, vendor products, are proprietary, but they're parameterized, and they bring them internal to the company, and they want to have an open standard of multiple vendors, and that causes this deparameterization in the logistics support. So how do we move towards a supply chain management which integrates with other security management areas? We want to make it look more like the G to E. So what we're going to do is we're going to include the other network types that we talked about in the management model: the operational network of devices and the ecosystem of organizations. By converging standards and control parameter to enable for multiple vendor integration, we then move to a place where only the internal to external is the focus. So we move C to G by providing an open ecosystem control on the different vendors. And we move from D to E by being able now to parameterize once they do come internal within the end user organization. And you see, by converging security management areas and the network controls of different networks, bring them together, we enable the management of products across the whole ecosystem environment to try and eliminate this ecosystem logistic contrast. The physical component industry designs traditionally rely on uniqueness and complexity of design as the product security, so kind of security by obscurity. For the most part, in the past, products were designed with the assumption they would operate standalone, so not really networked. So a lot of these microprocessor systems and industrial controls, your coffee pot, your microwave as examples, most of this product were designed with the assumption that they would operate standalone, not networked. So you have that F block where external to the end user company, proprietary designs are deparameterized, not designed to work together. These type of oppositions show up when these standalone devices are starting to bring in and placed on networks where they're really expected to support multi-vendors, so the open standardization, and they're parameterized onto the end user's network. So they have to be managed and synchronized, and have to have that management synchronization capability for the large-scale networks then. They just weren't designed for this thought in mind traditionally, and now we have to move towards this mindset. So security management is also going to address this mindset and this direction of use change. Another contrast of network types displayed by these adjacent opposite corners is this particular one that shows a contrast with kind of the policy and people area. We won't spend a lot of time on this for security management for critical infrastructure, but this is very important contrast in a lot of business aspects and how the companies interrelate based on the people. And basically, when proprietary information internal to a company lacks parameterization controls because they trust most of the people in the company. And a lot of companies are set up this way because they grew rapidly or just didn't think that there was a threat to everybody knowing all the information within the company, so they don't keep very many controls over it. In the world of open communications, though, it accents this loosely controlled business environment, because inside the company you have deparameterized environment and all the information is proprietary. But then if that would get outside the company through any means of network connection, different types of interaction, that needs to be parameterized so that everybody doesn't have access to it on the outside world. Social engineering is a big threat here, where people will continuously from outside the organization look to try to get information that should be parameterized and proprietary to the company. Corporate espionage, where companies are looking to get information from inside one company to help them maybe take it out to their company to help them make a competing product or make something that interacts with that product. Policy management in the policy management area is really the thought behind organizing these internal versus external and how we put controls across this boundary, this particular boundary, this adjacent quadrants which cause a lot of discontent in this area. So we're going to determine the interaction points of all security management areas, and we'll go more in depth in these in the next couple slides. On the GOROK security management model, we've identified network boundaries for each security management area and where they're needed to be addressed. So the policy management area looks at the actors and the process which requires for each of these interaction points from internal to external. So really looking at those two collection types of people and organizations. The security management model, which I put together by opening up the Cloud Cube model and showing the interfaces between the different blocks and networks and types of networks and what security management areas need to be addressed as the different boundaries are interfaced. And you see this largely focuses on critical infrastructure because that the main boundary in the center with the large, shown with the large arrow, is the primary focus security management areas for managing critical infrastructure. But yet this enables us to step back and look at the whole organization and the different types of networks and different types of boundaries that we cross and management of the different management areas that need to be addressed as information crosses those different types of boundaries. So nearly all of these contrasts show up in a critical infrastructure environment. Anytime that information crosses the network boundary type, we must manage the needs from that particular boundary. For critical infrastructure, the primary focus areas for security management would be different from information security or IT security. The main focus ones are going to be the supply chain, vendor product management, the trust management, the system integrity management, and this has to deal with those networks of embedded devices that need to trust each other. Secrets management, the coordination of all the distributed information across all the four different network types and how they're managed, things that are proprietary and secret to the organizations. And the data lifecycle management, how following the data from cradle to grave, including data privacy and its utilization, and managing the flow and the contrast and the security of those management as they cross these different boundaries. Secondary areas of focus we'll see on the next slide, but security management for critical infrastructure is largely focused on that large arrow in the center of the GOROK security management model. Looking at all the security management areas together, including the ones that are the main focus of critical infrastructure, you have risk management, supply chain management, vendor management, including product management, boundary and network management, including operational security management and patch management, secrets management, trust management, including system integrity management, data lifecycle management, including data privacy management and data utilization analytics, policy management, including regulatory management and standards management, and user access management. All these management areas we'll see come together as we further define these security management areas and the GOROK security management model. These security management areas focus on how business and security relate, and then continuous measures for maintaining the security posture in a business environment. So how do they relate? Security measures that are taken across the business relate to standard areas which can be managed. It breaks down those silos of operation within the company and organizations. Each security management area chains operations across the entire business and in many cases across multiple business organizations. Defines and standardizes data handoffs, interface points, and protocols for the process and technology solutions. Under continuous measures, we identify the touch points where operations in each management area require continuous intervention, and define controls for interdependent operations wherever multiple security management areas merge. Looking at roles of these different management areas in terms of information technology and industrial control systems. Under information technology, the business-focused areas would be policy management, risk management, standards management, regulatory management, trust management, are all kind of business people-focused operations. And logical-focused ones, supply chains, secrets management, and user access management, are all process and logistics-focused areas. And technology-focused, things that are actually handled by technology and information technology, boundary network management. This is a lot of the traditional packet management, firewalls, wire scanning, things like that are managing the boundaries between different technology areas. And in data lifecycle, things actually monitoring and managing the data and its privacy and its handling. In industrial controls, the business-focused areas are kind of the policy and risk. You see, under logistics focus, a lot of those have moved down, where standards now in supply chain management and regulatory management are more of a logistics focused, a wide range of lots of different products and networks and distribution channels. And technology focused really changes as user access management, secrets management, trust management, boundary management, and data lifecycle management now become more technologically driven. In systems of machine-to-machine communications and no people involved, you see everything kind of gets pushed down this list and things become more technologically focused. The effort and tasking where the most work is being done from security management areas under information technology, the people aspect, you see, many of these tasks are very people intensive. Operations that are done with somebody actually performing them. And the process ones, trust management, secrets management, are more of a process of how things are interfaced and interchanged, sometimes even between organizations is the reason why there's a process set up. And technology is very limited to the boundary management. This is why you see the IT information technology focus on boundary management, on packet monitoring, on firewalls, patch management, wire scanning is really a technology focus. And most of the work is done in information technology, and most of the focus on the security can then be done by technology. But most of the work and effort is done by people and things that get pushed over to the business side of the house. In industrial controls, you see user access management is still done by people, but there's less people. There's more systems and less people per systems, so it's actually a smaller task. And everything, once again, you'll see it be pushed down to technology, where policy management and risk management are still very people-driven. But process-driven, regulatory management, governance, and regulatory compliance with these processes, and actually using tools, because the massive amount of machines and systems that fall under compliance is growing with the amount of machines and machine-to-machine networks. And the same with supply chain and standards management. Get down to technology, and now there's so much data being produced by machine-to-machine networks and unmanned networks that data lifecycle management gets pushed down to a technology solution, as well as trust management has to be organized, because trust is no longer associated one-to-one person in the computer. Trust has to be managed in management systems, as well as secrets management and synchronization of these 4 different types of networks has to be managed. And boundary management still maintains a technology piece as similar in the information technology side of things. But now you see, as well with the people, process, and technology solutions, that industrial controls have to push more of those down to technology solutions. Now, security management areas converge on points which chain trust and accountability. The security management framework focuses on 4 trust accountability chains. The security management framework uses these trust accountability chains to bridge the security basis gap between critical infrastructure and information technology networks. Security management framework connects each of these trust accountability chains to the organizational governance and business needs. And the chains are sensor data networks, the data produced by embedded node systems all across these massive networks. The second chain, product lifecycle, the networks of distributed products, which are in many companies and at the end user organizations. Onboard system integrity, the sequence of controls of each operation onboard a single device, so how they're sequenced when they operate on that device. And network systems, the interconnection of multiple devices which are organized and managed to operate as basically as a single system. So these 4 trust accountability chains we'll look at a lot and really in depth for the focus of security management. Success of a company after the Industrial Revolution has been about how many products they could get to market and get people to purchase. A lot of that had to do with internally working on performance of the company. Margins on costs and profitability were continuously tweaked to optimize those returns and the cost of actually creating goods. Productivity and process improvement squeezed the organization to higher performance levels. Customers could easily change vendors for products who offered the best quality or price at any given time. So that was the kind of the competitive model of the landscape then. After the technological revolution, customer selection of products and thus kind of purchasing trends are not shifted so easily. The goal has shifted in the companies from optimizing a standalone product to attracting and retaining customers by offering products and services which all work together. So building an ecosystem of complementary products not only to lure the customers in, but to entice them to stay and buy more products and support and build their ecosystem. Though tweaking the margins and squeezing performance had really stayed as part of the manufacturing process, what keeps customers coming back is more of what they get long term. In many cases, costs are cut on the initial system to start the customers into this ecosystem. Supporting products then add value to the ecosystem and are not just standalone, they add value and add features and capabilities to the initial product purchased that they use to already get them in the ecosystem. So controls on product lines become more important because they are enforcing customer use patterns on distributed products out there are already in customer hands. And this type of a business model, especially in automated and electronic components, relies on cybersecurity base. We'll look at 2 very different management models and kind of contrast them. One, a product consumer driven, kind of the post-industrial revolution model. And secondly, a cybersecurity controlled management model. On the product driven, they use standardized components and open source. So this is really pushed by a lot of the open adaptability standards. On the cybersecurity controlled side, you look at more of a trusted component and application base, making an ecosystem that relies on knowing who you bring on board. On a product consumer base, and a lot of times the open source platforms, the PC platforms, the Android platforms, they get rapid growth and adoption by the customer base. Very quickly, lots of people were able to make applications and support them and support the whole ecosystem. On more of a security controlled side, you have a slower adoption, kind of like the Apple computer you saw took a long time to kind of build up their clientele and their market base because they were more selective their control of their environment from the beginning of their industry. On the product consumer side, you see a lot of really quick adoption of cutting edge innovation from really anonymous people out there. Any developer can make an application. Any manufacturer can make supporting equipment that all works in the ecosystem. On the more cybersecurity controlled side, you have the cutting edge quality, but it takes longer to build because you're more selective of who you let into the ecosystem and who you let work with your products. Both of them reduce cost on the entry product. They all have learned that to adapt in this post-technological revolution means getting customers on board. But on the first product, consumer-driven side, you really have an uncontrollable vendor base. You don't know who is making applications, who is making accessories that work with it, and that's the nature of that business. You don't want to. You want everybody to be able to really spur the growth in that industry and that product base. On the cybersecurity controlled side, you have a manageable vendor base. You only let application developers and electronic makers that you want to work with and you have verified their quality and their capabilities play in this ecosystem. For market and pricing control, the product consumer driven side, it doesn't have control over how many vendors are out there, what they're producing, has a very difficult time controlling the prices and keeping them from becoming saturated and over more products than sell in certain areas, which cause pricing saturation and prices to go down. On a cybersecurity controlled system and ecosystem, because you have all the vendors manageable, now you can start to say, I can control the numbers out there and keep them from saturating the market and then keep my pricing to a level that I desire it to be. It's about control here. On the product consumer driven side, the open source, they often open bill of materials. Anybody can build, can know what's in there. And supply chains, what happens is you get counterfeits that start sneaking into the supply chain of people who learn the bill of materials, extract the firmware, and boom, they can produce an exact duplicate without the research and development overhead that the initial company that makes the product ecosystem started it has put together. On the cybersecurity control side, the market size and consumer trends are traceable. So you can see where all your supply is coming in because now you have management and you know who the people to go talk to and say, what supply are you using and where is it coming from? On the consumer-driven side, the market size, players, and sales, all this are unknown to the ecosystem as a whole, and there's really no one controlling it, just letting it grow and develop to bolster the market and have everything grow as fast as possible. What happens on that product consumer-driven side is the parent company has a lack of control on the ecosystem, which leads to warranty and support costs on them for counterfeit products or for other ecosystem products that they did not produce and don't have control over, and a lot of times don't even know how they infiltrated into the whole ecosystem. On the cybersecurity control side, you have enforcement of use patterns for the whole ecosystem, end-to-end users. You can optimize your support and supply to find the best prices because you have control over it. What it basically ends up leading to is on a product consumer-driven side, you end up with a low-quality perception by end users. Not because the products of the parent company aren't good, but because there's so many different representatives and different faces to each product and different supports and non-supported products and fast products to market and different quality of different products. And it's all just uncontrolled. As part of the market to grow fast, you don't try to control those type of things. You come over to the other side, what you have is similar to what an Apple computer has done with their life cycle, their products. They have a high quality and a perception in those end users because they are able to maintain across their ecosystem all the various pieces of it to maintain a quality standard that they're happy with. So what is the end result of these two models? Well, we got to the point where you saw the product consumer driven side. You had a disarray business, kind of out of control support cost, loss of pricing control. On the cybersecurity control side, you have more of an organized business with optimized service, effective pricing control. What does that kind of start down the path towards? On the product consumer-driven side, shorter prime price on new products. So they put a new platform out, and they're not able to maintain pricing control to keep that prime pricing for as long as they used to be able to. So with this new product release, they only keep it for a year and a half. With the next one, they only keep it for a year. The one after that, only 6 months. And this prime pricing is uncontrollable and continues shortening. On the cybersecurity control side, the higher profit margins and longer prime pricing. So they're able to set their margins and keep that margin because they control the flow of how many products are out there in the market. On the product consumer driven side, you have inexpensive counterfeits that reduce the explosive growth rate. So the company that started this whole business model and not controlling the environment and being open started it to capture the explosive growth. And what happens is that company starts to lose the growth and not be able to control and keep the pricing for themselves. On the other side, you have the ecosystem controls. The expansion is traceable. The quality is traceable, and it starts to build a cult-like following of people who really respect the trends and the outcome of this model. On the product consumer-driven side, you have unexpected need to shorten development cycles. If you're not making prime pricing, you have counterfeits. All of a sudden, you start to say, oh, we need to get this next product out quicker than the last product went out, and you shorten those time cycles and you shorten money. So a lot of times you don't have the money from the prime pricing to reinvest in the research and development. On the other side, you're maintaining the consumer interest high through the next product release because you keep your prime pricing, until you've obsoleted your own product with the next version of itself. And you see on the product consumer driven side, you have a low quality perception after you have loss of support, shortened cycles, counterfeits, low quality perception, products, and poor support. On the other side, you've maintained your pre-explosive growth business model. You haven't lost, it hasn't leaked out everywhere to counterfeiters and easy adopters who have drained your profit model from the host company. So on the product-driven side, we're starting to reduce now engineering budgets, cut costs and cut employees and shorten the business. On the other side, we have high research and development costs. We have good budgets for our next products. Which one do you think is going to have a better next product? Now they've shortened that design cycle to get back to a prime price product, hoping that that's going to fix their business model, but it keeps to kind of incestual growing on itself. On the controlled side, we have the ability to maintain that business model that we had even 20 years ago. Maintain our current design cycles. We don't have to make a lot of scrambling changes, and we are consistent. What does it ultimately lead to? The product consumer driven side gets to a point where it starts collapsing on itself, kind of like a ship with a bunch of holes in it where it just starts leaking everywhere, and it's leaking profitability. On a controlled side, you get expanding business because you're containing a tight ship and you're not having things leak profitability from your whole business model across the board, because you have ecosystem controls, which basically are cybersecurity controls that are the basis of your business structure. For this newly developing Internet of Things, we're going to look at controls on products are enforced by cybersecurity, electronic communications and network authentication, software use restrictions and licensing, cross-product compatibility enforcement, service controls and product support authorization, networks of product chains, physical network electronic devices, people, and organizations. All four of the network types are interconnected when they exchange data. Interfaces within and between each network have touch points and handoff points for data. Each time data handoff is done, cybersecurity controls enforce, verify, and track these interactions. These touch points span across multiple organizations and industries. Cybersecurity controls at the interfaces between networks and organizations are the focus of the security management framework. These same controls, which establish trust, accountability chains, and bridge the gap between information technology and operation technology, also create a proven business model. So here we're linking with the security management framework all three portions together to control the business ecosystem.